Section 9.4 is radius of convergence. We've been starting to look at this graphically, and now we're going to look at some algebraic methods to tell where the radius or interval of convergence occurs for a particular series. We're going to do this quick review to look at limits and something about comparison of functions that we will be using. Find the limit of the expression as n approaches infinity. Assume that x remains fixed as n changes. So let's do the first one together. If n is increasing towards infinity, but x remains a constant, infinity over infinity just becomes 1. This plus 1 can be ignored because as n gets larger and larger, n over n plus 1 approaches 1. So this whole function, as n increases towards infinity, will just approach the absolute value of x. Take a look at the rest of these. Pause the video. It should only take you a couple of minutes. And put down what you get for your answer. Again, we're looking for the limit as n approaches infinity. This group, we are looking for a value n that would be a point at which one of these functions excuse me, would always be larger than the other. So the first thing we have to do is identify which, and it says the first series, and what it really means is the series that will become eventually larger than the second. So we want to know which one of these functions, 5n or n squared, will get bigger faster. So I think we can all say that a sub n is n squared, and b sub n is 5n, because at some point, as n increases, a sub n will always be bigger than b sub n. In this case, when n is 1, a sub 1 is still smaller. 2 squared is still smaller than 10. 3 squared is still smaller than 15. At 4, this would be 16, this would be 20. And at 5, they would be equal. So if n is greater than 5, or in other words, when n equals 6, since it has to be an integer, a sub n will always be larger than b sub n. So do the same thing with these. Seems to be, I guess that one's okay. We'll keep that one at the end as well. All right, so this is, again, pause, see if you can do the other three, and we will look at solutions in a moment. Okay, so let's go back. These should be the solutions for the first group. If you didn't get any of those, go back and look, and if you have questions, we'll take them in class. And this should be the solutions for the second group. This one, without a calculator, would be really tough to do because that's quite a large n value. But either way, what we're really looking at is which function at some point will always remain larger than the other function. Okay, the convergence theorem, this is what we're going to start with. There are three possibilities for a series with respect to convergence. First of all, there's a positive number r such that the series diverges for x minus a greater than r, but converges for x minus a is less than r. The series may or may not converge at either of the endpoints, a minus r or a plus r. We're looking at absolute values here. The second possibility is that the series converges for every x. In other words, r, or the radius of convergence, is all real numbers. The third possibility is that the series converges at a single point and diverges everywhere else. So therefore, the radius of convergence would be 0. Let's look at this terminology for a minute. The radius of convergence. R represents the radius of convergence. The set of all values for which the series converges is the interval of convergence. So, in other words, if the series converges on the interval -3 to 5, so everywhere from -3 to 5, then the radius of convergence is 4 units. This is 8 units long. The center of this is 2. So the radius of convergence from the center is 4 units, the interval of convergence is from -3 to 5. So this is a series that is centered at x equals 2 with an interval of convergence of -3 to 5, and therefore the radius of convergence, is 4 units. Okay? So when we talk about radius of convergence, we're talking about how far away from the center does the series converge with the actual function, and the interval of convergence is what numbers is that convergence occurring over. Okay, the nth term test for divergence. Now we're getting into some of our tests that we are going to be using to determine whether or not something converges or diverges. This is a very basic test. We always want to look at it first. The interval from the sum from n equals 1 to infinity of a sub n, any series, diverges if the limit of each term fails to exist or is different from 0. So in other words, as n approaches infinity, and we did some of these at the beginning, as n approaches infinity, if a sub n approaches or is 0, in other words, if it's getting smaller, the terms are getting smaller and smaller and smaller and smaller. So if the limit approaches 0, then the function, and I've said this backwards. Let me back up. If the term does not approach 0, if it is getting bigger or is approaching a constant, then the function diverges. If the limit approaches 0, then the function may converge. So this test is a test to eliminate the possible of convergence. It does not prove convergence, it only proves that something might diverge. But we do want to use this test. We're going to use it first every time, looking at what happens to the terms as n approaches infinity. If the terms approach 0, then we can go on and use another test because the function may converge. If the nth term does not approach 0, then we can eliminate all my other tests and just say that the function diverges. So this is the first test we use. The next possible test is a direct comparison test. So again, let there be a series with no negative terms. This is important. If the series converges, there is a convergence series where a sub n is always less than c sub n for all n greater than some integer. This was the second little thing we did in our little pre-warm-up. So if I can find a known series that is always larger termed than the series I'm starting with, and if this series, the larger one, converges, then so does the smaller one. The first series, the last choice, is that this will diverge if there is a known divergence series and if my terms are always larger than this term. So here's what we're saying. If I have a sum that converges, gets smaller and smaller, and mine is always below that, this is my c sub n and this is my a sub n, then mine will also converge. If there is some series that diverges and mine is always bigger than that, then mine also must diverge. So comparison test. If we can find a function that has terms that are always larger than ours, but it converges, then we can prove convergence. This has to be series without negative terms. All right, so let's do an example. So here's the series we want to prove. We want to prove that it converges for all real x. So let x be any real number. The series has no negative terms, so we're okay. Always raised to an even power and always squared. So for any n, my original term is always less than or equal to x to the 2n over n factorial. We know this because factorials increase faster than exponents. I'm going to rewrite the top function. So again, my function is always smaller than this. This is the Taylor series for e to the x squared. You see how important that list of known series is. You need to know what the known series are. Okay, so in our case, we found a function where we have proven that it is smaller than another known function if ours is squared in the bottom and the other one is not. Ours is smaller. And we also have found this as a recognizable function. We know that e to the x squared converges to e for the x. We know it converges for all real numbers. So since this series dominates ours, is always bigger than ours, term by term, then our series must also converge by the direct comparison test. I think I misspoke back here. I'm sorry. I'm looking for a series that is larger than ours for every term. So by eliminating the squared here, we have created a series that is always larger. This denominator will always be bigger than this one, and that's a series we recognize. All right, absolute convergence. If the series of the absolute value converges, then the series without the absolute value converges absolutely. Another just term here that we use. There's something we have talked about convergence. Now we're talking about absolute convergence. So if we can prove that the series with the absolute value around it converges, then the original series converges absolutely. And if the absolute value converges, then we can also say that ours converges. So if we prove it converges absolutely, then it also converges. So that's another way we can prove convergence. So let's look at that. So here's a series. We want to know whether or not this converges for all x. So we're going to take the absolute value of the series. I don't need to put an absolute value over n factorial because that's always positive. So now I have a series with no negative terms. Up here, I had a series that alternates, had positive and negative terms. So remember our original rule of comparison said that we had to have terms with no, or series with no negative terms. So by changing this to absolute value, we now have created a series with no negative terms. And its term by term is less than or equal to this series. Sine of x is always between 1 and negative 1. So the maximum value of this is 1. Therefore, ours will always be less than this. Now, this is, again, a known series that converges to E. Go back and look at that list at the end of section 9.2. Therefore, our absolute value, which we use to eliminate our negative terms, converges by direct comparison. So since this converges absolutely, it also converges. So in order to use a comparison, we put an absolute value so it wouldn't have negative terms. We know a maximum value for the numerator, which means I know that my function has to be less than the function I created. This is a known function which converges to E for all real numbers. Therefore, the absolute value of my function converges by direct comparison. And since this converges absolutely, it also converges. All right, let's see what we can do next. I think that's all we're doing for today. So after that, we will go on to some other tests, but this is all for this video.